have to do it. I got a 9.
All right, good morning, welcome back.
There's
A big thing, Sunday.
Sunday, okay.
First practice test. By showing up, you get 100% on a test lab and a homework assignment. Yes, it's this Sunday.
Wait, all of them? All 3 of them?
So I did not bring it, but I have a countdown sheet. We have 32 days before our AP exam. And that's counting weekends, 32 days. I know. You can bring, please bring pencils, you can bring calculator, and you can bring your orange sheets. And this is just a practice one that has no bearing on, besides the fact that it's required, and you get free points from me, but it doesn't have a grade based on how well you do on it. So it's good that you get practice on this. I will be sending out an email about this. If you're interested, down at Lawrence University, the problem is the timing's really poor or really good. I don't know which one. There is a practice exam down there, and they give you free pizza, and you work with some professors the morning of our final. So it finishes like at 11, and our thing's at 1. So you could easily make it if you're interested in getting that extra, or you could just stay for the review part and not take the practice test. They just do the free response. They don't do the multiple choice. So you sit and you go through and you learn from other teachers and or professors. I'll send you some information. But if you're interested in it, you're gonna have to let me know though, because I have to reserve you a spot. It's free.
So you said that's Lawrence?
It's Lawrence University.
How far is that? Well, Minneapolis.
Appleton, Wisconsin.
Oh, Minneapolis.
So it's 45 minutes from here.
Appleton, okay.
It's not Apple Valley in Minnesota. The same day as our actual final. So what is that, the 22nd? I think, the 22nd? So I'll be sending out an email today about that. I just got the information not too long ago. But if you're interested in doing it, it is free. But again, I don't want you to get tired out during the day either. Okay, so today, hopefully, I hope, because a lot of people viewed it, and now I can't find it, that you printed out the note sheet for Entropy and you looked through that. Because of days, sorry, I wasn't going to. I decided that I was going to give you the entire break, but then we had 2 extra days off, and we do have a ticking time clock that is in my head, at least, if it's not in yours. It's more of a time bomb, honestly. So the video was about entropy, so I want to review that a little bit, just talking about it. So what is entropy? Entropy, all the stuff that we're about to learn, we're only doing this for a week, and I don't have a schedule for you yet because everything got thrown way off kilter with the whole 2 snow days. Or let's call it 1 snow day and 1 Sunday. It was basically sunny all day yesterday. What is favored? What tends to happen in nature? So you know what? I will actually do, let's talk about cards. So what? I just have cards. What? I know. Okay, fine. Jeez. Good Lord, you guys, you're like my kids. I know. I've seen it once. Jeez. You couldn't even see half of it. I was cut off. You don't even know what was happening with it.
I see them already.
No, it's amazing. No, don't take out cards. So if you had atoms in this situation or this situation, which one would have probably happened first? Probably this one. And it goes to that. Nature doesn't tend to get more ordered. Okay? If you stopped kind of taking care of yourself, you probably wouldn't look cleaner and more put together. You probably wouldn't start smelling better. You'd break down. Your teeth would start looking awesome. As Luke checks it, so. Yeah. Bricks, if you throw them in a pile, they're probably not going to get all organized. They're going to get disorganized. You couldn't even see the magic trick that I was going to show. If you have highly ordered or highly disordered scenarios, this is probably the more likely scenario that's going to happen in nature. That's called entropy. This is my life. You have very low disorder or you have very high disorder. It's just the way it works. As we go in our lives, we get more and more disordered. Your body is gaining disorder until eventually all the systems don't quite work well together and we die. We gain entropy. We're gaining entropy. I know, bearer of fun news. As we go. And then this is on your note sheet, I believe. This is the Department of Entropy, and everything's breaking down as we go. So this is a sign or a way of figuring out if a reaction is going to occur or not. So a room from clean to disordered. This was on your note sheet. Things, if we're going to increase disorder, we're going to have a positive change in S. Entropy is S. So that is what's favored. We are increasing our disorder. So we could increase, again, this is all from the video, entropy increases when we have more gas, because gas is more disordered than a nice packed solid, right? We could increase temperature. Now that doesn't always occur that way, but usually if you increase it, things move faster. We're going to have more disorder. Simpler to more complex. My biggest thing I like to say is number of positions increases. What does that mean? This was in your note sheet. Number of positions increase. Here's a good example. This is dying. You increase your volume. By increasing your volume, if we pack everybody in a tight little elevator, or something, that'd be a big elevator, but in a very small room, and then we go into the field house and say, go wherever you want, you have so many more ideas and abilities to be in a different position that you increase the chances or number of different possibilities. And the more possibilities, the more disorder you can have. Another one is breaking down when something decomposes. So you have very organized white with black atoms, and now they're all broken apart. Well, you can have more possibilities. So number of positions. Whenever I talk about number of positions, if all of a sudden it's like, wow, they can have a lot more different scenarios or number of positions, that's higher disorder. And that's what nature wants to do. Okay? Nature is always going to go towards disorder. So I want to talk about being spontaneous today. So this, I looked it up. This is what it says on Google. And it says performing or occurring as a result of a sudden inner impulse. I didn't read all this, so I'm a little afraid now. Without any premeditation. Okay? So you can think of things as being spontaneous as getting your hair dyed, going to Vegas for the weekend. It's not as exciting as that for chemistry. So I looked up spontaneous. And these were the images that I first got. So, oh yeah, throwing up paper and running in the sun and whatever that guy's doing. And jumping, a lot of jumping. I'm splashing, I just went in the water. Oops. And then I found, I'm showing this, I had no idea what this was. Hold on, where are you? I probably missed it now. I'm getting scared actually.
Careful.
There was a weird one. Where did you go? I'm afraid to go up much higher. With your, oh, this one. What is going on? So, yeah.
Human combustion.
You can be spontaneous.
Human combustion.
Yeah, and that's kind of what it was showing. But anyway, that's not what we're talking about. We're talking about the last one, occurring without any apparent external cause. If something's going to happen for the rest of this year for chemistry, if something's going to happen, it's considered spontaneous. So if it naturally happens, I don't care if it happens in a second or if it takes a million years, if it naturally is occurring, it's being spontaneous. Okay? So, let's talk about the worksheet that you got just now, or the other neat sheet. It's called Free Energy.
There's this 300-pound woman that's sitting in a chair. And the fire department came. When we got there, we got things like pile of ashes. Her shoes, but her chair was not. Hey, that she insisted.
Okay. Oh, okay.
No, actually, I saw that on Mythbusters. They tested Mythbusters. That was with Mythbusters. What is this?
Okay, so free energy, what I'd like you to write in the upper left. It's actually called Gibbs free energy, and that's going to help you because, unfortunately, we are out of letters, my friends. The alphabet only has 26 letters in the alphabet, and we are already out. Entropy was S, enthalpy was H. I mean, these all just make so much sense. And free energy, unfortunately, is going to be G. So it's after Gibbs free energy. So the definition is, I wish I could give you words, but I can't. What this is going to do, before we get into it, free energy is the true ultimate sign of whether or not something's going to happen. If you're confused or I don't understand the entropy part, I don't understand what you're talking about. All the things we're about to do is, will this reaction occur? Will this situation naturally occur in nature, in the lab, or not? And free energy is the ultimate guide of that. It's something spontaneous. And free energy is a relationship between the two other indicators. Okay, we have enthalpy and we have entropy. So, and did I write that backward? No, I didn't. So you have your enthalpy, you have your entropy. We're going to make a bigger, we're going to box this in a second. This is not the actual equation that I want. But this is going to be change in G. Okay, so when we have a change in G, we're going to talk about whether or not it's spontaneous or not. Free energy is like energy. And if something's going to occur, usually it loses energy. It goes to a lower energy state. So, when it's positive or negative, this is going to be non-spontaneous, and this is going to be spontaneous. When it's a negative sign, you're going to have a spontaneous reaction. That's the most important one right there. So when it's negative, it is spontaneous. And units are important. It's not going to be tricky. I'm going to show you today. We're going to do some calculations today. If we don't get to everything that I gave you at the beginning of the hour is not necessarily intended to get through today. It's today and tomorrow, depending on where we're at. Okay. You don't have to memorize units. You'll have an idea, or it'll tell you. So ultimately, this is what we need. And you can keep that change in G. I'm just going to rewrite it all as one thing here. This is the ultimate guide to whether or not something's going to happen. And you can get confused and allow yourself to get worked up about the words free energy, but this is what I see. It's the change in my heat flow is the energy going in or out, that's enthalpy. And then I'm going to subtract temperature affecting the disorder. How much disorder am I changing through that reaction? Am I gaining or losing disorder? And it's a relationship between those two things, and we're going to kind of look at that today. So there are a couple little issues. One says watch out for units. Unfortunately, enthalpy is usually in kilojoules, and entropy is usually in joules. So I'm going to write this, but honestly, you just got to be in the same. So you just got to be careful. Just know the very fact that one of them is usually, entropy is very small, enthalpy is a lot bigger usually. So you're going to have different units. So just be a little bit careful. Something we're going to see in a couple of our calculations in a second is when change in G equals 0. When that's the case, we're not gaining or losing. We're not changing. So we are at a thing called an equilibrium. So if that's the case, right, if this becomes 0, more or less what it happens to be then, if we look at the equation, is that change in H equals T change in S if I manipulate that just a little bit. So for you, it's really easy, more or less. That equilibrium happens at phase changes. So you could go solid to a liquid, or you could say the word boiling. Well, then that means it's a liquid to a gas. Because what did we learn with heat curves and cooling curves is that you're not actually gaining or losing energy. Right now, or the temperature is not changing. Now it's about putting that energy into changing and overcoming those attractive forces. So let's do an example. Oops, one lesson. Also remember that you have an element in its standard conditions. So for example, if you have O2 or N2, bless you, or even just AR, just making up some things. If they are already at their standard conditions, we look those up. You don't remember that? Those are always 0. And those are going to be on that blue sheet that we're going to look at in a minute. You don't have to memorize things, but sometimes they don't give you a value because that's a 0. So I want to take a look at this first one and just show you how it's used. It says, what is the boiling point of a solution where you have the entropy of vaporization? It gives you the heat flow. So that's positive, so it's going in, it's absorbing. And you have a certain disorder, okay? So how does that work? Well, first thing I want you to do is underline boiling point. It's a big deal. The reason why, oh, come on. Oh, well, hopefully, I probably can't move anything right now. If you look at the equation that we just boxed, there we go. When it says boiling point, that means it's probably looking for temperature. It's looking for a temp. So if I'm looking for a temperature and they gave me change of H and change of S, wait, I don't have temperature and I don't have G? Like, you can never have two variables that are unknown, right? So you have to take a step back and go, oh, wait a minute. One of these I have to know. Well, and I really stress this now, a boiling point is a phase change. So that has to be 0, okay? So if I'm talking about this is the first thing I did think about. And the reason why is that they gave me both of these, so that has to be the equation. Well, then that has to be 0. It has to be 0, because it's a phase change. Again, guys, a lot of this, I hate to say the phrase, but this is plug and chug. You're going to have equations. You just have to take a step back and just understand what are you been given. We'll talk about meaning and put more meaning on it, but sometimes there's not as much meaning as it needs to be. I can go either way. Because I have joules already, let's make this joules. So that's my H. I'm just writing it down. If you need to make an extra note or underline or emphasize that you have the same units, go for it. Minus T times my enthalpy, or entropy. So then I solve for it, and I got it for you. It's high. Temperature's going to be 681. So what it's just saying is that's the boiling point of this liquid and/or gas with that enthalpy of vaporization and that amount of disorder. There's not much to it. There's not a lot of meaning to this. That's just execution. Okay? But let's put a little more meaning onto here. Let's talk about to me, this little table is probably one of the most important things for you, is the meanings of the signs. So you're going to have negatives and you're going to have positives. And sometimes, I gave you a little practice sheet. That was a quiz about 3 years ago that I gave. Like, this was the test. So just understand that. The one that's sideways and has 2 different problems with all open space. And you have to be able to look at values and say, yeah, this means this, and this means that the reaction is going to go this way, or whatever. Signs are important. So, first off, let's just talk about this in generalities. Change of H, that means heat flow. I'm just going to write this on the side as a nice little review. So are you gaining or losing heat? Okay? So, what have we learned about that? Which one is more natural? Do you gain or lose heat? Usually lose, or you could say energy too. Usually you lose energy, right? So to be spontaneous, that's what we're going to make. So a check means spontaneous. Write that underneath, because we're not going to write it on both. Like, if we put a check mark, it means it's spontaneous. So that means that it is more favored, or usually a reaction loses energy. This isn't always the case, but in general, a reaction usually, when it loses heat, that's considered spontaneous. I have my change in S. That's disorder. Right? That's what that basically means. I'm not writing down the word entropy. It doesn't mean anything to you if you can't continue to remember it as a disorder. So disorder, things go towards being more and more disordered, right? More and more apart and gaining positions. So a positive, this is probably the hardest part of this, is just keeping track of all this. A positive entropy is probably more favored. So then my G is my free energy, and that's still not going to have a lot of meaning to you. So think of it again this way. This is the ultimate guide. It is the ultimate guide. It looks at both. It looks at both, because sometimes certain things can be favored with a positive change of H, depending on the reaction. But usually everything is always favored with disorder. So I think of it this way. Energy is like heat. And if I'm releasing energy and that's favored, then shouldn't be, or heat being released is favored. So my energy overall energy, if it's being released, can be favored. So change in G, if it's negative, the reactions automatically can be favored. And this is the one that matters the most. This is the one. If that is negative, it doesn't matter what the other ones are. It is that one. That is the king and the queen and all of it together. So I'm going to show you right now on the bottom what it all means. And I'm going to grab my sheet just so we can make this a little faster. So I already have it right here. I don't know if you want to rewrite it again, but I'm just kind of showing you what I'm trying to say here. You can kind of guide what you want here. You're going to run into situations. Now I don't have a number. If you wrote numbers in here, you'll know every time. You plug it in, does G become negative? If it is, spontaneous. If it isn't, not spontaneous. So let's just talk about it though in the most general terms possible. And I look at this. The one that jumps out, which one is not spontaneous automatically? And there's all these signs, but there's only one that's the easiest thing to identify. That's not spontaneous. What's the one that dictates it all? Free energy. And free energy must be negative. So the bottom one, right?
What is G considered if it's 0? Is it negative, positive?
Neither. It's not. We're not having any change, so we're in limbo. It's a good question. Yeah, we're transitioning phases, so it has to be pushed one way or the other, or else you are stuck right in the middle. Okay, so good question. What happens at 0? At 0, what that means is like you have a closed bottle, and now you are evaporating and condensing, and that level stays the same. So you aren't going one way or the other. So if you're boiling water, you say, well, that's a phase change. Yes, but I am boiling it, and I am not. It's going all the gas, and it's not coming the other way. So I'm moving past that point in a moment. You know, I just need to boil all that down, but I'm above that temperature, or I'm above that. I'm moving past that phase. We'll try not to run into those too often. That's a hard question to answer in one without an example. This one right here, because of the positive, this is an automatic no. It's not spontaneous. It's the simplest one on there. So that means all the other ones are spontaneous. But let's talk about why. Which one is the ultimate yes? Which one follows the check marks above? Which one is the yes? It is no matter what. The second one? Because you have a positive, negative, negative, right? So this one's the yes. Those are the perfect situations. Okay? If you look at them, they're opposites. But truly the only one that matters is the change in G. So the other two are yeses. But we need to talk about why. Okay? So we're going to write yes way on the left. But these depend on the temperature. Okay? So I want you to think about this. If this is going to be negative, so if this is going to be negative, and I have a negative number here, what must this be to make sure this is negative? If you have a negative and you subtract the number, because I'm making this a negative. So this needs to be at a very low temperature. This has to be a very small number. If that doesn't quite, like if this was a really, really high number, this is the hard part, you don't know the numbers, but if this is a really, really, really high number, and you multiply it by a negative and you subtract a negative from a negative, you actually could get a positive number. So this would have to be at low temperatures. This one, to get this to be negative, this one will make more sense to you. This is already positive, so I need this to be a huge value to get this positive to become a negative number. So I would have to make this a very high temperature. Because these are both positives, so I need to subtract this value. This has to be a very big number to make sure that that's a negative. Those aren't as important. The second and the fourth one, you understand, okay, these are perfect situations. This is not favored. This is extremely favored. So, I know right now you're like, I hate this. Let's take a look at what you actually need to do, and you'll start liking it a lot more. So, on the back, I have some equations. These are ones that you can use. Okay, these are the ones that are going to be on your orange sheet, and we're going to do 3 examples. And by the time you're done with this, you're going to be like, oh, this ain't as bad as it all. All right, first question. It says calculate the change of S, change in H, change in S, and change in G for the following reaction. Use the appropriate appendices. So sometimes they'll say this, I'd underline that in your book to find individual values. Okay, so let me show you. Number 2. Okay? Number 2 says the sum of the products minus the sum of the reactants. We have done this. You did this with enthalpy using those blue sheets that I asked you to pull out. Okay? So what we're going to do right now is we're going to do that again. So look at this. It says, what is my change of H, change of S, and change in G? Well, if you look at your blue sheets, there are some columns. And if you look at them, there is H, S, and G. Okay? So what we're going to do is do this a little bit differently, and I have my numbers here as well. But the minute they talk about all these, you should be thinking about this. Okay? That's always that's the mother question, or the equation. So, if it's telling you or gives you a table, because you won't actually have a reference sheet, that's never going to happen. So you'd have like these kinds of data on the beginning of your questions. Then you should recognize, oh, it's products minus reactants. So for example, let's do the H. Okay? I looked these up. So I want you to just kind of look up a few of these with me. Actually, you know what? Let's do it this way. So then you can see any notes. I'm actually going to write down what they are. So under SO2, let's find sulfur dioxide on our sheet. So I'm assuming it's on the back. Under sulfur. You got to be kidding me. Oh, there you go. Like it's not even there. I got words.
Negative 300.
So I'm going to round up. Do you see? Is this not negative 297? Correct. And that's kilojoules, right?
Oh, trash.
Or am I wrong? Usually enthalpies in kilojoules. All right. Sam, I like the stash of it. And then the entropy, is it about 248? Or not? Because sometimes they're a little different. Am I wrong? Okay. Okay, then I can trust my numbers. Okay, so now we're going to just do each of these systematically. I can't calculate with this, but for notes, it's nice to just see. Okay, oxygen, guys, enthalpy, to create an element from scratch is always 0. You can look it up, but that's from a long time ago. You don't make, and you got to remember, what you're looking at are the numbers reflect making SO2. So this actually is S plus O2 gives you SO2. And then it's how much energy these take to make that. And that's that number. So it takes no energy to make oxygen when you're already at oxygen. But everything has a disorder. Everything has a certain disorder. So if you look up for oxygen, it's 205. And I'm not going to write units again because I've already done it once. And I'm just going to help you out. SO3 is this and that. So, that being said, this is not difficult. All you need to do is products minus reactants. So, for example, the change of H equals negative 396 minus, oops, and I got to multiply that by 2, sorry. Do that again. It's the products minus the reactants. Do I have to include the 0? Not technically. I'm trying to just show you what the heck I'm doing though. And that's going to be, can help you out because I want to try to at least get through these problems today. What is the change of S? Same thing. Again, how would you know you have to do this? Because you're going to be given values. Like there'll be a little table in a chart. The minute I see that, I get really excited about that because I know I'm probably going to do products minus reactants. It's not going to be all that difficult. If you ever don't show you one, probably 0. Enthalpy for elements are 0. So then I do the same concept for the second one. Except it's just going to look a little different because I have actual 2 numbers. Please, it's not about memorizing units. Understand that? The units are going to be on the table or on the chart. You just mimic it. So the issue for me is that I have joules and kilojoules. So now I'm going to plug these in. I have change of H. I have change of S. Now, can anybody tell me what temperature I'm at? What are all those temperatures at? They're at standard conditions. This is important to remember. Standard conditions mean room temp. Room temp is 25 degrees. If you don't know that, does it say, maybe it says it on the top on the other side. I'm not sure. Actually, I'm curious. Does it on the front?
No.
It may not. Does it say it on the short sheet?
Yeah.
So you do need to know that though. So I'm going to plug it in. Here we go. I'll do a different color so you can see it. I need the same units. If it doesn't say it, I always like to go bigger than smaller. For some reason, it's just me. I don't know about you. But I make more errors going this direction because sometimes you have to add a 0. But going this way, usually people make a lot less mistakes. It is your call. I'm not saying that you have to do one or the other unless they tell you you have to do it. See, you don't have to worry about units because the units are there, they cancel each other out. All that's left is going to be joules. So I have change in G. And let's say you had this question and a follow-up question was, is this spontaneous? How do you know? Does this naturally occur without any interference or help? So is it? Why? G is negative. That's all you need to know. If G is in the equation, nothing else matters. S's and H's, they take care of themselves. It's over. Now, if you do look, this is the problem, right? That's favored. This is not. Entropy is actually getting more ordered. And the reason why, you could have guessed this beforehand, we'll talk about this, but if I just gave you this equation, I said, is this gaining or losing entropy? You know already. This is important. I know I'm giving you a lot, but we need this today. You went from 3 moles of gas to 2 moles of gas. You're getting more ordered, right? You had 3 moles of gas, now you only have 2. It's getting more organized. So that's why entropy is actually going down. But there's a lot of heat flow that's being lost. So this heat flow overrides that disorder, and you have entropy. Enthalpy will always dominate over entropy because entropy is usually a smaller number. So this is spontaneous because of this. I can see it in our eyes and everything else that don't make conclusions that you're done and you don't get it. Like, you got to just hang on to everything you can. I'm trying to give you the examples to get you through this. Okay, so again, if you haven't figured out by now, it's really late in the game, but almost every AP question, they give you hints, or they give you an example, or they give you a situation. It's not from scratch. So you kind of have to take what you're given and then work with it. Okay, let's take a look at example 2. It says, consider making ammonia. They give you the equation. And then they give you already the G. Calculate the value of the equilibrium constant. Can you look at that and go, God, I have no idea. Well, equilibrium constant is what? It's a K. If you look up on top, there's only one equation. And unfortunately, there's a lot of meaning behind this stuff, and I will show you that, but sometimes it is just about finding the right equation. And there's not much more I can say about that. So you have, I believe there's only one at the top, unless if I'm not remembering what I put there. Oh, well, there. It's the same situation. You just solve the different parts. So here's my equation. My free energy equals, basically, and what do we always say? K is dictated by temperature. Temperature changes K, so that's why temperature is involved in that. So we're going to plug this in. Now I know I'm assuming, yeah. We could have done this one right there, but I kind of wanted to show you the beginning one instead. So here we go. If I do an R, does anybody remember without looking at our orange sheets, which you don't have to do that, but the R value that has joules in it, 8.314, right? And it's joules per moles Kelvin. So if it's joules, our joules and kilojoules have to match. So if I'm given kilojoules, that's not okay. So I need I have that up top too?
Maybe.
I do. That's fine. It says watch units. My temperature is 25 degrees, so 298 Kelvin. As always, if you're sitting there going, when am I supposed to do Kelvin? First off, if you don't know Celsius or Kelvin, you probably just do Kelvin. But the easiest answer, you always look at your constant. If constant has a Celsius, use Celsius. If constant has Kelvin, use Kelvin. And then I have natural log of K. So I'm looking for K. So yada, yada, yada. You divide some stuff out. That's my next mathematical sequence, just to give it to you. So what do I need to do with my calculator? I need to take that to the E, right? E, or not, that's probably worded incorrectly with E to the, so let me show you that. E to the 13.44 K, and I get follow-up question. What's favored, products or reactants? Is K greater or less than 1? Greater. What is K? K is products over reactants. So if my number is greater than 1, products or reactants are favored. Products. I could have told you products were favored anyway, but I'll tell you why in a second. Can someone tell me, in this infancy of us learning about all this, why I already knew that products were favored? Why did I already know the reaction was going to go to the right? It was going to move forward? Why do I know that? I can word it differently and I give it away, but why do I know the reaction is going to move forward? Why do I know the products are favored? Because...
You're going from 4 to 2 moles?
Hmm?
You're going from 4 moles to gas.
That's entropy. That's true, but I'm not. Entropy isn't the true dictation of if reaction will go 100. G is negative. Well, how do you know it's going to go to products? Because that's the natural progression. It's always going to go to the right. That means it's spontaneous. If I make products, it's spontaneous. So the fact that it's negative, my K better be greater than 1. So if I had a positive G, my K better be less than 1. Because that means the reactants are favored. So it's not a spontaneous reaction. Again, there's all sorts of things, and they may ask you that. Guys, it's as simple as that sometimes. How did you know it's spontaneous? The answer, G is negative. That's sometimes the answer. Like literally writing that. Okay, let's look at example number 3. It says calculate the value of change in G for the following reaction. Gives you temp, and it gives you concentrations. Ugh. Okay, so.
Get K out of there. No. You can find K.
Whenever they give you amounts,
Just draw nice lines. Don't hold it. Just draw.
so they gave me amounts of all these. So the question is, where am I, right? Like, what am I making? So I don't know if any of you are thinking of this.
I mean, you can find K. Oh, yeah. That's that question.
Right? I mean, those are some questions that I have. So, can anybody tell me what letter I'm talking about when I'm writing all that stuff in red? When I don't know where I'm at? When I have amounts, but I don't know where? What? It's a Q. You're like, oh God, come on. I'm trying to get away from all this stuff. It all stays together. That's Q. So, if you look at the equation above, all the equations above, I don't know if I have that on the side. Yes, I do. On the lower right, it has Q. Sorry, my pen just broke in half in my pocket. I'm wondering if there's ink everywhere. We are going to basically have this equation. Oh, sorry, 1 second. So, let's first get Q. Let's do this quickly so we can get to our final stuff today. As a reminder, It's always good to see it again. That's how I would get Q. This is not as common. Some of the other questions that we're going to be doing are much more common than this. Okay, but if I plug this in, I just put in the numbers. It's nicer. Got this. That's just my Q. Okay, so now, here's a little bit of a trick. And I wouldn't call it a trick, but it's, we're not asking, we're kind of going to take a little bit of a derivative of this. We're not asking what the actual final G is going to be. It's asking, calculate the value of G for the following reaction right then, like where we're at, like right at that moment. So, we're going to just plug it into my Q, and then we're going to use the temperature, and then we'll calculate that, okay? So, the tricky part actually is sometimes is, if you were, sometimes you do need to know K. It's not always, I guess, when I go, I'm going to take a step back from one moment with Hunter saying, well, G is negative, and then I said, well, if Q is, if K is always positive, then it's automatically going to be favored. Unless if the K, if you had a Q and you had to drive it, Q's not K. So what if Q was too big or too small and it had to drive it to the other direction? Well, then the reaction is going to occur until it reaches K. But if you actually know your K, that's different. And I know I'm probably confusing you a little bit, but Q is different because Q can move. K is wherever it's supposed to be. So when K is large, it's going to be driving it to the right from the beginning. But if you were finding Q, well, I could be way over here, even though it's positive, and I have to drive back and make reactants. All right, I could have a really large, a really big negative, but I'm smaller than my K, so I still have to drive it this way. So sometimes that's a little confusing with that. So let's plug that in. We don't have two G's because we don't have the other, oh, we do actually have the other reaction. I paused. So this is of the actual reaction. And that is white. Okay. That is the actual reaction. So this is the one at standard conditions. And what was that? Well, that was given in the previous problem. Okay? This is under normal conditions. So that's going to be my actual reaction. Come on. So I'm going to put that in joules. When in doubt, is it just 33? Oh, 33. Is it 33.3, right? Yeah. Okay. Still at 298, I hope. Awesome. Cool. And I need a natural log in that, sorry. Jeez. I'm out of space. That's natural log of 0.6804. I do not have an answer for this one. Again, this one's not used as much. Usually it's H's, S's, changing T's. Negative 32, 5,
Yeah.
4.
Oh, yes,
I'll do this. I changed it into kilojoules instead of having it in joules. Now, is there such a thing as being more spontaneous or less spontaneous? Well, the more negative it is, the more favored it's going to be. So this isn't quite as favored, but it's still naturally going to occur. So those are some of the equations that we're going to be doing. Let's take a look, if you could, at your worksheet that I gave you. As a stable line. We're going to wait. Tomorrow we're going to be working on that little quiz in class. I'm going to go through it. I'm going to give you all the answers. It's not an actual quiz. Don't freak out. So the one with the staple, it just says entropy and free energy on it. Okay, what you guys are going to have to do is a lot of it's multiple choice, and then you are just picking answers. Okay? Did I make it this Monday? Okay, this should go kind of quickly once you start doing it. And we probably will have a quiz on this next Wednesday, so you'll have an idea. We'll keep practicing it. So, a couple things just to point out as we go. And I suggest starting this tonight. Number 2, I'm just giving you some hints here. I'm not actually doing all this for you. So, by the way, number 1, it says which of the following represents an increase in entropy. So you're looking at which one gets more disordered. So let me just say what letter A. And if you need to make, like when it says explain, writing things on the side of the other ones can help. So for example, freezing of water. What are you doing? You're going from a liquid to a solid, correct? So aren't you becoming more organized? You're becoming more packed, more organized. Whenever you go towards a solid, you're being more organized. Whenever you're going to a gas, you're becoming less organized or more disordered. So A is not the answer because you're not increasing your disorder. Let me show you, like, look at letter E. You're going from 3 moles of gas to 2 moles of gas. So you're going from more gas to less gas. That's more order. Okay, that's not increasing entropy. And what I'm hoping is this worksheet is kind of a working tool for you. Like, and if you have any questions at all, the way that I did the answer key, I explain a lot on there. So anyway, you probably have already figured it out on here. Maybe not. Number 2, the enthalpy though is, they give you a number and it's at a boiling point of 64.2. So enthalpy, so that's my H. It's not a bad idea to write above certain numbers. So I got 35.3, that's my H. And they gave me a temp, okay? And it says calculate the entropy, so it's saying change in S. So right there, without really thinking too hard, this is again the equation that I'm using the most. The minute that enthalpies and entropies are showing up, that's my equation. Here's the problem. I'm looking for entropy, and what else don't I know? G. So there is a clue in here. What did we have? We had a problem where we had 2. So usually when you don't know both, G is usually 0. Why? Boiling point. There's a boiling point. If you want to underline, just underline the boiling point part. That means that change in G equals 0. That's a phase change. So right there, I got my 0. Now I can solve for T. I mean, sorry, S. Okay, let's go to 3. Again, I'm just giving you some ideas to recognize this, because once you do this, I remember this every year, whenever I had to do this, and every year with students, you guys, right in the beginning, everyone has the same look on their faces, and then they start working on it, and they're like, oh, this isn't as bad as it looks. Look at how I've given you values already. It says calculate the entropy change for the following reactions, and then there's values there. Well, that's simply your products minus your reactants, right? That's all you're doing. Make sure that you're doing the moles, right? So you have half of an oxygen. Right, so you do the brackets, right? So we're going to have a bracket, and then we're going to have that. Right, that's what it's going to look like. Right? For number 3. So I want to actually do, what do we have? Is that fast or slow too? Isn't that slow? I mean fast?
49.
No, it's fast. It's so fast. I want to do number 4 completely, or as many as we can here quickly. So, letter A, you help me. In which of the following reactions do you expect to have a decrease in entropy? Meaning what? That you're going to gain order or lose disorder. It's always confusing because you can say either way, right? I always like to talk about it with disorder though. You're getting less disordered, more ordered. Confusing. So letter A. If you're going from a solid to a liquid, Are you increasing or decreasing your entropy? Aren't you increasing it? Isn't it getting more disordered? Right? Remember, going in that direction, going towards gas, you're getting more disordered. That's not what it's looking for. Right? You're gaining positions. They're not as organized. The atoms are more loosely packed. So now a word. There we go. Letter B. In this one, are you gaining your... it looks like you went from 2 particles, 2 different compounds, 2 elements, and now you've combined them. So that's potentially decreasing my entropy, right? I went from 2 to 1. Right? That looks like it's getting more ordered. Like there's less possibilities. I don't have 2 different random atoms, I have 1. Letter C. That I went from a solid and a gas to just a solid. Right? Isn't that potentially also I'm bringing this one up on purpose because seems like there's more options here. I went from a gas to a solid. I lost my gas. So that's letter C. Let's talk about D. Again, this is just, it's a conversation. A liquid to a gas, that one's easy. When I go from a liquid to a gas, that's majorly increasing my, right? And if you're like, what am I supposed to write? I actually write like liquid to gas if you're trying to explain it just for yourself, right? You're gaining more disorder. And then lastly, again, for letter E, I know that I'm just making observations basically, what you see, but again, the minute that you gain a gas from nothing, or from something else other than gases in the first place, again, when they're all gases, you gotta look, you have more or less of them, then you're gaining disorder. So we only have these 2 options. That's it. So if you have to break a tie, then you got to go with the one that's going to be the most the most disorder. And in this case, what's it asking for? Again, decreasing. So okay, here I went from 2 solids to 1 solid. Very organized to very organized. Here I went from a solid and a gas. I had a gas, and now I don't have a gas at all. So by far, this is going to be the answer. You don't have enough information. Yes, it probably was getting a little more ordered because you went from 2 solids to 1. But honestly, the packing of the atoms could be the same. But you lost the gas. You went from having a gas to no gas at all. Gases are extremely disordered. So if you don't have a gas now, you've just gotten a lot more order. So that would be the answer. One last quick thing here. I know we're getting close, but we're good. Go to number 7 on the back, please. I'm going to give you a helpful tip. So let's take a look at this one. It says, at what temperature would a given reaction become spontaneous? The minute I see spontaneous, I need to at least be thinking, I write this above the word spontaneous, change in G. Why? Because change in G is the ultimate indication of whether or not something's spontaneous or not. So check it out, they gave you H, and they gave you S. So this is probably so it's asking what temperature? At what temperature? So, maybe one of you can help me out mathematically. I'm solving for this. And again, I know these 2. So let's go back to this thing. You can't have 2 variables, right? But this doesn't say it's at a phase change. But here's the trick. If I make this be a 0, and I solve for T, what does G need to be spontaneous? Needs to be negative, right? So all it has to do is tip it. So if I get a number, I'll make up a number. All you got to do is figure out, should it be greater or less than that temperature? Does that make sense? All you got to do is, like, let's just say you found out to be 100. Well, if it's 101 or if it's 99, would it make that go to a negative number? That's basically what you have to figure out. So would it be greater or less than the answer for your T? So big message is, if you don't know 2 different things and one of them is a G, you're probably going to assign that a 0. But in this situation, you need to recognize, well, it's just asking at what temperature would this be spontaneous. So I would make G equal my 0. We'll definitely answer some questions. I'm telling you now, you can do a lot of this. You really can. Start going through it. I expect that you have tried and maybe gotten through 2/3 of this tonight, because this is all you have from me. Any late work, any tests I wrote to you, tests and lab makeups due by Tuesday, only because we've had 2 days extra off. So let's get that taken care of. If you have any other extra credit or missing work, I do apologize, just the way it worked. I do have like 3 columns yet. I'm going to try to get all that stuff in, but it's mostly just homework. If you know you hand your stuff in, it shouldn't be an issue. I can't go over those other quizzes yet because not everybody's taken them, but I have had those in the grade book, so you can see how you
That
do
would
it.
do more bad than good.